Hello, everyone. I am a master candidate from Shanghai Institute of Microsystem and Information Technology. I appreciate the opportunity to share something with you. Well, the topic I'm going to share is SD pose, Structural Discrepancy Aware Category Level 6D Object Pose Estimation. 6D object pose refers to the rigid transformation matrix from the object to the camera space, consisting of 3D rotation and 3D translation. It is widely used in robot grabbing, autonomous driving, VR, AR and other scenarios. 6D object pose estimation can be divided into two categories according to the target level, instance level and category level. The instance level approach can only estimate the pose of the known instance and requires a CAD model. Relatively speaking, category level can estimate the pose of the unseen instance from known category without the limitations of the CAD model. As a result, category level approaches are more versatile and challenging. Wang et al. Were the first to propose a category level pose estimation task and introduce normalized object coordinate space, NOCS, a shared canonical representation for all possible object instances within a category. However, due to the huge intra-class variation, this severely limits the performance of pose estimation. To solve this problem, Tian et al. Propose a category prior-based approach. Although the SPD has achieved sound effects, there are still some unresolved issues. The first problem is that for different input instances, when the structural discrepancy between the category prior and the instance is enormous, the error of pose estimation is large. To address this problem, we use their mutual structural discrepancy for shape supplementation to augment the learning of intra-class shape information. The second problem is that there is noise in the observation point cloud obtained from the depth map after semantic segmentation. For this problem, we fuse additional speech information to remove the effect of noise. Our SD pose pipeline is as follows: input an RGBD image, and obtain the corresponding image block, instance point cloud and category prior after offline mask RCNN processing. Then we obtain the corresponding features through the feature extraction module. Then IEA module is utilized to supplement geometry features. After that, a SDF module is employed to fuse semantic and geometry features. By stacking multiple IEA and SDF modules, the final instance and category feature are generated. Next, we reconstruct the instance Knox model and establish the correspondence between the observed point and the Knox model. Finally, the 6D pose is recovered by estimating a similarity transformation. The IEA module aims to learn structural discrepancy between the instance and category prior for shape supplementation. Specifically, IEA takes instance geometry and category features as inputs to learn geometry relation matrix A, thus calculating the structural discrepancy features according to A and enhancing their original geometry features. The SDF module reduces the impact of noise and improves network robustness by fusion additional semantic information. We employ two different fusion strategies. The first one we call semantic immediate fusion, SIF, and the second one we call semantic dynamic fusion. We compare the proposed method with other methods on CAMERA25 and REAL275 datasets. From the table below, we can see that our method realizes a more significant improvement on the REAL275 dataset, which contains more previously unseen instances, than on the synthetic CAMERA25 dataset. Furthermore, we performed a quantitative comparison of the visualization results with SPD. We can observe that our method produces a more accurate pose than SPD, especially on geometrically complex objects, for example camera category. This indicates our SD pose can sufficiently learn the shape change by utilizing instance category structural discrepancy to supplement geometry information. In order to verify the efficacy of the critical components of our method, we conduct ablation studies for IEA and SDF modules. The baseline is SPD corresponding to row 1. By comparing row 1 and row 2, we can observe that the performance of all metrics in row 2 has an overall boost. This demonstrates the effectiveness of our IEA module. Comparing the results in row 2, row 3 and row 4, we can observe that SDF is a better choice. That's all. Thank you for listening.